Now that we know conceptually what drives per worker capital accumulation over time, we can take the next step and link it to output. Substituting the production function into equation 11 in the last slide deck accomplishes just that. Let's quickly review. The change in capital per worker KT plus 1 over N minus KT over N equals investment, which is really just a fraction S of output per worker, represented by F of KT over N, minus depreciation delta times KT over N. There's really nothing new here. The only difference is we substituted in the production function for saving and investment. Intuitively, an economy will add output per worker when savings per worker exceed depreciation and vice versa. Having this information in hand, we can graphically illustrate the long-term behavior of output per worker, capital per worker, and depreciation per worker, which is sort of our workhorse model in thinking about growth in the Solow world. This graph plots out per worker, it puts out output per worker, on the vertical axis against capital per worker, K over N, on the horizontal axis. The curved line on top, this one here, is simply a production function. Note that output strictly increases the more capital a worker has available, but less and less so as the capital stock increases. This is simply the law of diminishing returns in action. Think about this again in terms of our hammer economy, which is illustrative. If I give the average worker the first hammer, if I'm somewhere down here, output increases a lot, so we jump up a lot on the vertical axis. If I add another hammer, output increases some more, but not quite by as much. Now, if the average worker has 19 hammers, adding one more is still going to contribute positive output, but only a tiny bit. This line then illustrates diminishing marginal product of capital. Below the production function, down here, we have savings investment per worker. Because saving and investment are a fixed fraction of output S, the function simply behaves proportionally, but is less than output itself. The rest then goes to consumption. For instance, if this were 80%, the remaining 20% would go on to consumption. Finally, the straight line here is depreciation. Depreciation is simply a linear function of how much capital per worker there is. For instance, if the depreciation rate is 2%, at $1,000 of capital per worker, $20 would depreciate each year. If it is $2,000, $40 would depreciate per year, and so forth. So the more capital there is, the more of it breaks each year. That should be intuitive. To summarize this one more time for your reading pleasure, because this is really the core of the dynamics in the Solow model. Output per worker increases as capital per worker increases, yet at decreasing returns. Capital accumulation per worker increases proportionally with output per worker. And then finally, depreciation per worker simply increases at a linear rate with capital per worker. Without having to explicitly model time, the simple graph tells us something about the dynamics of capital and output. A country with a low level of capital per worker displays a high marginal product of capital, large investment, which depends on output, and investment at this point will then simply be larger than depreciation. That implies positive capital per worker accumulation, and the economy will grow. Output per worker will also grow. However, the more this goes on, the higher the capital per worker stock becomes, the more the marginal product of capital will fall, and eventually additional investment will equal depreciation. Of course, if a country has a very large capital stock per worker, it can work in the opposite direction. Now, graphically, any capital stock to the left of this capital stock K star over N, if you're somewhere over here in the lower range, is in the vicinity of is in an area where investment, this line here, is above the depreciation line. That means investment is larger than depreciation, meaning that capital accumulation per worker has to be positive. But the more we grow, the more the capital stock moves to the right, the less and less additional output investment's going to generate, and eventually it's just enough to offset depreciation. By the same token, if the capital stock is very large, if you're to the right of this level K star over N, investment is generally smaller than depreciation, and that means the capital stock is going to shrink over time. The marginal product of capital then is actually increasing because we now have less capital, And eventually they're going to move to the same position here where investment is exactly equal to depreciation. Now, what does this imply? For one, convergence. This is really where this idea of convergence comes from. Countries that have grown for a long period of time, like the United States, for instance, have a lot more capital per worker than countries that have started growing later or have only, really not been growing much at all. If you think, for instance, China as an example, which in modern history has started to grow much later than the United States have. And the general idea then is that because the marginal product of capital is higher when the capital stock is low, countries that haven't been growing for a very long time should grow faster and they should catch up to already developed countries. Now, as I mentioned at the beginning of this discussion, the evidence doesn't actually support this consistently. There are some countries for which this has been the case. South Korea and Japan are usually the textbook examples. So clearly there's more going on than this. But the idea of convergence simply results from the law of diminishing returns. That's what you should take away from the Solow model here. The second thing this implies, and this is perhaps the most important takeaway, is that an economy can only grow based on investment by building more capital as long as the marginal product of investment exceeds depreciation. And it will have to fall eventually because there's only so much capital you can add to, say, the labor force before the additional capital doesn't do that much in terms of production. All of this discussion implies then that there should be what is called a steady state level of capital per worker. It's the K star over N that we've seen before. It's called a steady state, not so much because it's an equilibrium, but because there is something like a stable situation in which growth is no longer driven by investment. Right? The idea is when investment no longer adds to the capital stock, it should not actually cause economic growth. This should be intuitive based on the hammer example as well. So if the model is a little bit too abstract, uh, think about this obvious insight that no one really needs 18 hammers to build anything, right? Once you have the appropriate number of tools, additional tool investment is something that really only serves to replace obsolete or depreciated equipment. Formally, a steady state is reached when savings investment equal depreciation per worker. On the left-hand side, we have the savings amount, the investment amount at the steady state capital stock. Here we have the level of depreciation at the steady state capital stock. And for this capital stock, we can also find output per worker, which is simply whatever the production function tells us output per worker would be equal to. What are the main takeaways from the basic Solow model? For one, investment, or generally speaking, accumulation of any productive factor with declining marginal returns cannot explain long-run growth. There's only so many hammers you can add and expect the economy still to grow. Now, since productive factors are complementary, this really affects all physical production factors, since, two, there is the law of diminishing returns. So as long as there is a single productive factor, in this case it's labor, but it could be capital, it could be knowledge, whatever really you can think of, it means the other input factors will have diminishing marginal returns with regards to that one factor. Right? So if I have a fixed number of workers, I can only give them so much education, I can only give them so much capital to work with, I can only give them so many natural resources to work with, before adding more is not actually going to help us produce more. Right? This is the fundamental insight why investment is not really what's driving growth in a long time. A third, perhaps less obvious corollary to this discussion is that an increase in the savings rate does not create long-run growth. And this is something that matters from a policy perspective because things like, for instance, Social Security are policy choices and they affect the way a country is saving. Right? If, for instance, you privatize part of Social Security, that meant that individuals would have to set part of their income aside that would effectively increase the savings rate. It's decisions like that. But if you start in a given steady state, if you increase the savings rate, the only thing that's going to happen is the savings function is going to shift upward. That does imply a new steady state of capital per worker that will be higher. And to get there, the economy must grow for some period of time. However, as the economy is doing that, as output per worker expands, the law of diminishing returns still kicks in eventually, and that will cause a new steady state. The consequence of that is that per worker capital and output will increase, but that they will not keep increasing forever. So savings cannot create long-term growth. So the savings rate does matter. It matters in the sense that it will increase the overall level of output, but it cannot cause long-term growth in the way we've experienced it, for instance, in the